Okay, so welcome to our second week. So I think I told you this before, but this course has two parts. The second part will involve some calculations. As an engineering course, there will be some equations involved, and we will be using those equations to calculate certain numbers that define the performance of an aircraft. But the first part of this course is more descriptive. So the purpose of that first half is to make you understand how a general conventional aircraft works, how it flies. And before we start using the equations, I will try to make you understand where those equations come from and why do we use them. So we're still in that first half. So if you remember, in our last lecture, I started talking about the main elements of a conventional aircraft. So let me just quickly over this presentation. So remember, I said for a conventional aircraft, the dynamic lift concept is used, and I will be talking more about how this dynamic lift is created. But basically, for that to work, the aircraft needs to have a forward velocity at all times, such that necessary aerodynamic forces are created that can carry the weight of the aircraft. So in that case, it needs to be moving in the x direction at all times. And whenever you need to change the direction of the airplane, you need to rotate it first. So whenever you need to go along the vertical axis, along the z-axis, you cannot move the airplane directly along that axis. You need to rotate it, as you see in this animation. And then once you point the nose of the aircraft in the direction you want to go, your forward velocity will be taking you in that direction. So these rotations have special names. The first one was called the pitching motion. This is called the yawing. And then the third rotation is the rolling motion. And then I said everything pretty much in this course is related to conventional aircraft. And by conventional, we mean the regular aircraft that you know, right? So if I ask you to draw a picture of an aircraft, most of you will just draw a conventional airplane. You will draw a fuselage, you will draw wings and some tail surfaces. So this is what a conventional aircraft is. And so these are some examples of unconventional aircraft designs. Then I started talking about the elements of an aircraft. I started with the fuselage and showed you some sample fuselages from different conventional aircraft. And then I showed you this unconventional design. By the way, I found the video of this aircraft flying, so let me just stop here and show you quickly that video.
Another intriguing German design.
So this has sound as well, so let me make sure that you can hear the audio.
Another intriguing German design, the Global Voss VV-141 reconnaissance aircraft with its offset crew compartment. Although the prototype showed potential, the concept was considered too unconventional, and it never had its use.
So I don't know if you noticed that they say in the video the design was found too unconventional, so that's one reason it didn't go into mass production. So obviously there were other reasons as well. But the main advantage of this design is the pilots sit here. They have a clear view, so they don't have the propeller in front of them. But instead of this airplane, there were two designs studied at the time in Germany, two competing designs for the same purpose. And this was one of them, which we saw in the video. And the one they chose is this one. You see, this aircraft has the same advantage. So let me see if there's a bigger picture. See, this has the same advantage that the pilots have a clear view, but it's symmetric, right? It's more conventional in that sense. Okay, anyway, let me get back here. So this is the engine, and there was the cockpit before that. Okay, so this is where I stopped. So in this course, one of the assumptions we make is that the aerodynamic forces are developed on the wings only. So even though every single part that is exposed to atmosphere contributes to these forces, we just make the assumption that these forces are too small or they just cancel each other out. And what remains left is the forces on the wings. So therefore, wings are the only thing that we include in our computations. And at this point, we need to somehow extract some numbers from the designs of a wing. Okay, so while making performance calculations, we will be using some equations, and into the equations we can only put numbers, right? We cannot put the shape of the aircraft directly. We need to somehow extract numbers out of that wing design. So in the wing design, you can take a very detailed shape of the wing. What I'm saying is you can get precise coordinates from the wing design and use them in the design, or for simplified equations, you need some basic numbers instead of the entire shape of the wing. Some basic numbers are sufficient in our calculations, and these basic numbers they are all shown in this diagram. So here we're looking at the wing from a top view. So the general shape is called the wing planform. So this shape you see here, which is a trapezoid, is called the wing planform. So I talked about the chord length and the wingspan. And I said that one of the most important parameters is the aspect ratio, which is defined with this formula here. And then there's one other ratio which is called the taper ratio. This taper ratio is the ratio of the tip chord to root chord. So in other words, it's the ratio of this length here, the chord length at the tip, to the chord length at the root. Okay? So for example, if you have a rectangular wing, then the taper ratio for that wing will be just 1, right? Because if this is your wing planform, this is the center line, your tip chord is equal to the root chord, so these are equal. So this gives you a taper ratio of 1. Or if you have a triangular wing, then in this case the taper ratio is just 0, because you have the tip chord is 0. So for this one, the taper ratio is 0. On this diagram, you see some sample wing planforms. So these are not scaled properly. So this is the wing planform of the Wright brothers aircraft. So as you see, it's just a rectangle. So this is the F-18 aircraft. It is a trapezoid. The Concorde wing platform is triangle. I will be talking about this Concorde aircraft quite often in this course. So this was the only supersonic passenger airplane that was flying, and unfortunately it's not flying anymore. And being able to fly at supersonic speeds is very critical, and throughout the course I will be talking about this Concorde airplane. So this is the Boeing 747 aircraft. It's again in the shape of a trapezoid. This is the wing of the space shuttle. It's called a compound planform because it's composed of two different geometries, as you see here. Okay, so I think this is enough about the wing planforms. So I will continue with the elements of an aircraft. So the last item was the wing, main wings. And then for conventional aircraft, there are smaller wing sections at the tail. So this is the vertical one. This is called the vertical stabilizer. So let me just read the definition here. It's a fixed wing section whose job is to provide stability for the aircraft, which means helps the airplane keep flying straight. The vertical stabilizer prevents unwanted side-to-side or yawing motion of the aircraft. Okay, so at this point, I think our only option is to have 10-minute recordings. Okay, so I was talking about the vertical stabilizer. So basically, let me just try to quickly explain how this vertical stabilizer works. Okay, so let me just draw an airplane, a top view of an airplane. So these are the wings. And then there's this vertical stabilizer here. So I say that the airplane needs to have a forward velocity at all times. Okay, so if for whatever reason the velocity of the aircraft deviates from its x-axis, this may be due to a side wind, for example. Suppose that there are some strong winds coming this way, then these winds will change the orientation of the airplane. Okay, so all of a sudden the aircraft will start going in that direction, which is something you don't want because this creates additional problems. So anyway, in this case, this vertical stabilizer, the purpose of that wing section is to make the aircraft go straight again. Okay, so with the help of this vertical stabilizer, the aircraft's orientation will go back to be going straight. Okay, and then there's a moving section at the back of this vertical stabilizer, which is called rudder. The vertical stabilizer itself is a fixed surface, but the little part at the back is moving. So this can be moved to the left or to the right. This is a small moving section at the rear of the stabilizer that is attached to the fixed sections by hinges. And because the rudder moves, it varies the amount of force generated by the tail surface and is used to generate and control the yawing motion of the aircraft. So basically, the pilot can control this moving part, and by changing its orientation, the pilot can change the amount of force created on this wing section, and that causes the airplane to rotate in the yawing axis. Okay, so just like you see here. So this little black part is the rudder, and as you can see, it moves with respect to the vertical stabilizer, and that change, that motion changes the forces, and as a result of the change due to Newton's second law, motion occurs, right? The force creates acceleration, which creates motion, and in this case, the force creates a rotational motion because the force here has a moment arm. So this is actually shown here. So you have this force, aerodynamic force, and this is the center of gravity of the aircraft, and there's this moment arm, and that means this side force creates a yawing moment with respect to the center of gravity. So now let me go back here. Here you see some examples of vertical stabilizers, the different designs. In this case, you have two vertical stabilizers, but they're not really vertical anymore. They're inclined with some angle, as you see here. So as opposed to having a single large vertical stabilizer, they put two of them. So the main advantage here is having a large stabilizer has problems. Having a large surface means it will have to be heavier because you have to make it stronger. So one of the disadvantages, it has to be heavy. Also, a large stabilizer will be creating more drag force. Drag force is the one that you need to overcome by the engines. So if you have a larger drag force, that means you will have to burn more fuel. It will be more expensive to fly. So if this airplane could have a single vertical stabilizer like that instead of two, as you see in that figure, but like I said, this would have to be larger, and having a larger vertical stabilizer is not something you want. And also there's another disadvantage to having a large stabilizer, and that is so this is a fighter airplane, and large surfaces means that aircraft will be easier to detect using radar waves. So this is a stealth aircraft. That means the radars cannot detect this airplane. And if there was a larger vertical stabilizer here, it would be easier for the radars to detect this airplane. Here, there are three of them, three small vertical stabilizers. So this is an older design, obviously, and I don't think radar detectability was an issue here. But obviously, they prefer to have three smaller vertical stabilizers instead of having one huge vertical stabilizer. And this is an unmanned design. There are, again, two vertical stabilizers, and they are pointed down. You know, most vertical stabilizers are pointed upwards, but in this case, they are pointed downwards. So these are just three different designs. Okay, the rudders are traditionally controlled by the feet. So if you are flying an airplane and the airplane has a rudder, which really should have for you to be able to fly it, you can control rudder with your feet by using pedals. So these are two pedals the pilots can use to change the rudder position. And this is the cockpit of the space shuttle. So I think this was Atlantis, but I'm not sure. Normally, space shuttle obviously don't need a rudder while in the space because there's no atmosphere and there's no aerodynamic forces at all. But while landing within the atmosphere, the space shuttle flies like a regular airplane, and in that case, it uses rudder for yaw control, and the pilots use the pedals, as you see here. Okay. Now, let's move on to the horizontal stabilizer. So this is very similar to the vertical stabilizer, but its purpose is to keep the stability of the aircraft on the horizontal plane. So let me come back here and let's take a look at how that works. So let me just draw. This is now the side view of an airplane. So this is the vertical stabilizer, and then there's the horizontal stabilizer here, which I didn't really draw nicely. So again, your aircraft is flying straight, and due to many reasons, the orientation of the aircraft may be disturbed. One example can be, suppose that this is a passenger aircraft. This doesn't really look like it, but let me just try to draw a passenger airplane. Okay, so there are people inside this aircraft, and this has a certain center of gravity. This is the center of gravity of your airplane. And suppose that all of a sudden all the passengers just moved towards the back of the airplane. So the people within the aircraft walked towards the back, and that shifts the center of gravity backwards, right? And naturally, this will disturb the orientation of the airplane. The airplane will try to go nose up. So the nose of the aircraft will be going rotated upwards. At this point, the horizontal stabilizer will just bring it down. So without pilot having to do anything, the existence of the horizontal stabilizer will try to bring the nose of the aircraft downwards. So by the way, I will be talking more about how this really works. Now I'm just explaining the purposes of these elements. Again, I'll be talking with more detail as to the operation of these elements. And just like the vertical stabilizer, on your horizontal stabilizer you have a moving section, and this moving section is called the elevator. And by moving this elevator, you can change the amount of force on the horizontal stabilizer. And as you see here, this force has a moment arm with respect to the center of gravity. And this moment arm creates the pitching rotation. Okay, so let's continue. Now let me show you some sample elevator designs from different aircraft. So I think this is Boeing 727. So anyway, as you see here, the horizontal section is above the fuselage. So it's at the tip of the vertical stabilizer. So this is a more conventional design where the horizontal stabilizer is at the same level as the fuselage. And this is an unconventional design. So here you have the horizontal stabilizer at the nose of the aircraft, not at the tail. And at this actual surface is called a canard. So this is a short wing-like surface projected from the fuselage of an aircraft. So the purpose is the same. It works as a horizontal stabilizer. So let me say a few words about this example. So this is the F-16 aircraft. And if you notice that the entire horizontal stabilizer rotates, so this doesn't have a separate elevator. So if you look at here, this part here is the elevator, and this part is only moving. Whereas in the case of F-16, the entire horizontal stabilizer rotates as the elevator. And that's because this is a supersonic aircraft. So to be able to control the aircraft at supersonic speeds, what you have to do is you have to move the entire horizontal stabilizer. Otherwise, just an elevator like this is not effective at very high speeds. So this is just one of the reasons why flying at supersonic speeds is very difficult. Okay. And then we have one last control, and they are called the ailerons. The ailerons are placed at the trailing edge of the main wings. So there's one here and another aileron here. And they work in opposite directions. So the elevators, you deflect the elevators in parallel. So if you deflect this one downwards, then you deflect the other one downwards as well. But in the case of ailerons, you deflect them in opposite directions to be able to get roll control. So by deflecting this upwards, you change the force here, and you deflect this downwards, and you change this force here, and the change is in the opposite direction. So this is reduced, and this is increased. And as a result, you get a net rolling motion. That's why they are deflected in the opposite directions. That way you get the rolling motion. Okay, now okay, so this is the inside of a Boeing 747 airplane, just prepared to take off. And I said the rudders are controlled through the pedals, and the elevator and the ailerons are controlled through a stick in the cockpit. So I think it's called yoke. I'm not sure about that at this point. But so anyway, the pilot has this device in front of him, and he uses this to control the elevator and the aileron together. Now this is for elevator control. The aircraft is not moving yet. So before the flight, the pilot is just checking that the controls are working properly. And now he's testing it the other direction. Now he's testing the aileron control. So this may look like a simple test, but it's very important. so there are some very strict regulations for aircraft control, and you have to follow these procedures before every flight. So this is one of them. So before the flight, the pilots are required to make these checks to see that aircraft is functioning properly. So otherwise, you don't want to find this out when you are above the ground. You don't want to find out that your aileron control is not working properly. So that can result in a serious accident. In fact, there was a real accident here in Ankara. A CASA CN-235 cargo airplane crashed in Ankara, in TAI actually. And it was due to after the maintenance, for some reason they misconnected the aileron controls. So the pilot control that's supposed to make the aircraft roll towards right had the opposite effect, because the left and right ailerons were misconnected, and because of that the airplane crashed, and I think 3 or 4 people died as a result of that. So to be able to prevent such accidents, it's a very simple test, but the pilots have to actually make this test. So this is for thrust control. So there are 4 engines here, and there are 4 levers for that. So the pilot gives full throttle, the engines start producing thrust, and that causes the aircraft to accelerate. And the pilot just starts controlling the airplane. So he pulls this stick towards himself to make the aircraft go nose up, but the deflection is so small that it's hard to see in the video. Okay, so the question is if the ailerons are the only devices that create roll motion. Well, they are the main controls devices for rolling control. That means they are the most effective, but you can make roll control using some other devices as well. Spoilers can be used for that. So basically, for roll control, you need to arrange forces such that you get a net rolling moment, right? So let me just go back to that diagram here. Okay, so you need to somehow make forces such that you get a rolling motion, you get a rolling moment. Okay, so you need to have somehow, for example, more force here and then less force here, such that will give you a rolling moment. The ailerons is the most effective way of doing that. But for example, you can use these surfaces here. I will be talking about them later on. And these surfaces can be used to make that difference between the two sides of the force on the two sides. Some airplane can use this as well. Normally when you deflect these elevators together, they give you a pitching moment. But if you deflect them in different directions, then these can give you a rolling moment as well. But these are just secondary roll control device. The major one is the aileron. Okay, so I will actually keep talking about these airplane elements. So I told you that for dynamic lift, you need to have a forward speed such that you can get this lift force to make your aircraft go balance its weight. And if you think about that, if you need a forward velocity, then the magnitude of the velocity should matter, right? So if you go faster, then you'll have larger force. In fact, we know that from both analytical equations and from experiments, these forces are proportional with the square of the speed. So that means if you increase your speed by a factor of 2, then the forces will be increased by a factor of 4. So this is the dependence. So this symbol means that proportional with. So the L stands for the lift force and D is the drag force, and they are both proportional with the square. Okay, so this is a known fact, and when designing an aircraft, you have a target weight. Okay, so you want to carry a certain amount of weight. So that means you need to create that much lift force, and at the same time you want to go as fast as possible, right? Because the main advantage of air travel is it's much faster compared to going by the railway or highway. So if you are flying, then you want to go as fast as possible. Okay, that means you need to have a certain wing design that will carry your aircraft weight while flying at that speed. The problem is you cannot always fly at that high velocity, especially while landing. You have to slow down. So while flying high in the atmosphere, if you are flying at, I don't know, 900 kilometers per hour, you cannot land your aircraft at that speed. That would be too difficult, right? For one thing, you would need a very long runway to slow down from that high velocity. But obviously, trying to land with such a high velocity would be very difficult. So what happens is, while landing, you have to be able to fly at a much lower velocity. For example, for typical passenger airplanes, these are some numbers. So for cruising, passenger airplanes typically fly at 900 kilometers per hour, but while landing, they slow down to 300 kilometers per hour. And since the forces are proportional with the square, that means the lift force you get while landing is 9 times lower than the lift compared to the lift force during cruising. So you need to, but you still need the same lift force because the weight of the aircraft doesn't change. Just because your velocity changes doesn't mean that your weight have to change. Your weight is still the same. So that means you need to have something, you need to do something. So you need to be able to carry the weight even while flying at such a low speed. So what people did to overcome that problem is they made these so-called high-lift devices. So these devices are used to increase the lift force while flying at lower speeds. So you see some examples here. These parts located at the trailing edge are called flaps. So this is the trailing edge of the wing. So this is the trailing edge of the Boeing 747. They are called flaps. Again, later on I will be talking more about how these can change the lift force. And certain aircraft have similar devices on the leading edge. And if these devices are on the leading edge, they are called slats on the leading edge for increasing the lift force. Okay, so this is the slat, and these are the flaps. You see some sample designs for these high lift devices. So this is a plain flap. These are different designs. And you see this is much more complicated. There are multiple parts And for large aircraft, you need such complex designs to be able to carry such a huge weight at low speeds. So this is the cockpit of a small aircraft. This little thing is used to control the flap position. So the pilot uses this little lever to make the flaps extend or retract. And for a Boeing 747, this is the flap control lever. So the pilot uses this to change the flap positions. So let me show you some videos here. So this is Boeing 727 aircraft. The flap operation is shown on the ground. So if you notice that the flap operation is slow, the reason for that is this is not really used to control the motion of the aircraft. This is only used to increase the lift force as the speed of the aircraft goes down. And since the speed change is gradual, you want the lift increase to be gradual as well. You don't want the lift force to be increased immediately. So that's why the flap operation is slow, as you see. So it takes about a minute to go from the fully extended position to fully retracted position. And I have another video showing these flaps extending in flight. Okay, so this is an aircraft approaching the airport. So as it approaches the airport, it starts slowing down. And as it slows down while flying, as you can see in the video, the flaps are extended. Okay, now it's extended even more. And I think there's an aileron video. So this is taken from the same video, but it's really hard to see. The ailerons are here, and they move by a very small amount. You have to really pay attention to see them moving. So the deflections are just on the order of just 1 or 2 degrees, not more than that. The next element is the spoilers. The spoilers are placed on the upper wing surface, and they're intended to reduce lift in an aircraft. So the flaps and slats are used to increase the lift force, and these spoilers are used to decrease them, because there are times where you want to decrease the lift force, and for that purpose you use these spoilers. It can be used to slow an aircraft or to make an aircraft descend if they are deployed on both wings. So spoilers can also be used to generate a rolling motion if they are deployed on only one wing. So this is an answer to that question earlier. So if you deploy a spoiler on one wing only, then you can create a rolling motion as well.